Hello, 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 hello. Welcome back. Thank you so much for coming here as we try and clobber our way through the end of this one and move on to the next one. I hope you're all doing well today. On this a wonderful Sunday, end of our weekend here. Put that away, put that away. Okay, I got all this other stuff going on here. Too many open windows. Okay. Okay, and then we put open that, and hello. Okay, cool. So it does work. Neat. Sorry, I was I'm trying out a new there's a mod adaptation, whatever you want to call it, for OBS here, and I was just checking out to see how well it worked. So it does sort of work. So yeah, that's good. Okay. Anyway. Yeah. So the plan for today, we are actually most of the way through with this paper. Music that starts too loud compared to the voice in general. Okay. Good to know. I will edit that. Give me 1 second. I'm going to switch back to see which channel that's running on, and then I will turn it down. So give me 1 second. All right. Is that better? I can put it down more, but is that a little better? By the way, I appreciate any yes, awesome. Thank you. Yeah, any feedback or anything like that, super appreciated, because I have a lot of this stuff muted as I try and get it to run, and so I'm mostly going off of the feedback you guys give me to make it, to improve things and make everything better. So right, so the plan is to finish this paper, and then I found something that's a bit more wordy. It's about similar subject, right? But it's a little bit more wordy and might be good to help do a conceptual. It's also a research paper, so there is that piece, but it might be a little bit more conceptual in terms of how it's operating. We'll see. Like I said, I found it. Just doing a quick scroll through the paper looked good. Yeah. So we'll roll with that. Again, I'm sorry for Friday. I just had too much stuff going on in the background that I was trying to get done for I've got a paper I'm trying to put together and slides for a presentation, blah 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 blah. So I apologize for Friday. Friday was a little nuts for me. Next Friday we should be back to our normal schedule here. Okay, so just to review what we were looking at last time, just to get an idea. So let me scroll in so we can see this a little better. All right, so we were looking at different mode absorptions, right? So the ordinary. So normally on Friday I do stuff associated with research. So it's a little less guided like these papers are, and a little more free form. I'm just trying to put stuff together and figure out what works, kind of thing. So it's usually what I try to do on Fridays. As I said, this past Friday I was just in crazy land, so I unfortunately was not very functional when it came to doing Friday. It's on Friday evenings. Yeah, so that's typically what we do Friday. So that's why I try and have the two. I try and have the paper oriented one on Saturday, which may or may not be like science and math focused, could be philosophy, could be something else. And then Friday is definitely more of the heavy math. I'm really trying to figure out what the hell's going on. My brain doesn't operate kind of day. So, and then of course Wednesday is typically reading. So, that's usually what's planned. But all right. So going back a little, right. So we're looking at further comparisons, full credit. Okay. So we're trying to compare these approximations that they have, and so they're doing these plots for the different modes. This is the yeah, it can be. So I spent some time trying to do trying to understand the path integral stuff and a few things like that. I did a bunch of stuff with the set of the class of equations for which the Wigner distribution is one of them, as is I'm forgetting the name of the class of equations. So it's Wigner distribution, the ambiguity function, Fourier is essentially a subclass of these. So they're transformation functions, essentially, where you have a specific kernel and then a setup as to how the transformation operates. So we went sort of in depth into that a bit. Actually, you might have some experience with the Wigner distribution. Turns out there's so sorry, I'm going to go down one of my little rabbit holes. Turns out there is a connection between the Wigner distribution and the so-called ambiguity function that's used in radar engineering to determine your uncertainty in Doppler versus uncertainty in location of a target off which you've bounced RF. They're actually double Fourier transform away from each other. And so my idea was to try and use an analogy to the path integration in the Wigner distribution that can be used in the Wigner distribution. Try and see what that did in the ambiguity function. Yeah. Yeah, I forget. There's like a whole class of functions, and I can't remember the name of them off the top of my head. That might be it, but so yeah. So it was to try and, since it's a it's a double Fourier transform away from an ambiguity function that's used in this very different other field. I was wondering what the analogy would be of that path integral thing. So anyway, so I was doing that kind of thing on Friday, a little more mathy intensive stuff. Hi Toasty, good to see you here. But yeah, so that will we will continue on with that as normal this coming Friday. Yeah, last Friday I was just like, I'm dead. This ain't happening. But anyway, so where we were in this paper, right? We were looking at the index of refraction, which of course is telling you how the radio wave is moving through the plasma that's in the upper atmosphere, how that changes in this more realistic versus an approximation that was more typically used before modern computation became big and powerful. And so the question is, where is this approximation useful, right? And so we have these plots that kind of show when the approximation goes off the rails here, right, compared to the actual whoops, oh boy, what did I do? There we go. Right. So we were seeing this interesting behavior when the signal frequency was equal to the plasma frequency, right? We were seeing that it almost looks like the phase response of a what's it called, a resonance, which is kind of makes sense again, because you're sort of you're starting to resonate at the frequency, you know, along with the same frequency that those electrons are moving around. So that sort of made sense. And then let's see, where do you go from there? He was looking at what was the A graph? Okay, he was looking at the loss curves. Right, because the K was the coefficient of absorption, so that's how much energy you're losing into moving these electrons around, that they bounce into each other, that the energy that you've put into it becomes heat, so you've lost that energy in your signal. And so it's looking again at the difference between those in the approximation versus the final, or the more in-depth plot. And this is, in other words, you know, where can you use this approximation? So that's where we had gone before, and we stopped before we really got to the results and discussion. So this should be interesting. We should be able to finally see the conclusions that they've come out of with this. Okay. So figure 1, A through D, that was the first set of images above. Okay, you can see it. By the way, if something is not visible or I'm writing off the screen somewhere, let me know. It's an unfortunate habit to have. So the mu was the real component, right? I'm forgetting the convention here. Hold on. Let me see. If I'm remembering, I believe mu was... yeah, chi was the imaginary piece, right? Yeah. I'm pretty sure that's what it was. Yeah. Yeah, mu was the real part of the index of refraction, and chi is the imaginary part of the index of refraction. So if you want to think of it functionally, mu is telling you how your wave's going to move through the medium, and chi is telling you how your wave is going to get absorbed by the medium. Esque, sort of. Okay. So, mu ordinary longitudinal, or extraordinary, right? These are the two different modes that are propagating. It splits into these two different ways that the signal propagates, are reported for different values of the theta angle. Again, theta is the angle between the incoming signal and the Earth's magnetic field lines. Okay, having considered a radio wave with y equals y. Okay, so y is the so again, this is the what's it called? Transverse versus the longitudinal. So this is how much of this is in this direction versus in this direction, right? Is 0.5. So it's about halfway between the two, right? So half your energy is kind of going in the longitudinal direction along the line of that B field. Half of it is going perpendicular to it. Kind of think of it that way. All right. Frequency equals 4 megahertz, and a minimal collision frequency. So that's the collision frequency in the plasma. So that's your electrons bouncing into other things, how often they're bouncing into things, because that's, again, how it's taking energy out of your radio wave and putting it into heat are those bounces. right? That kinetic energy transfer. Typically of the high D region around a latitude of 90 kilometers. So again, this is the upper region of the bottom layer of the ionosphere, which maximizes the absorption variance among the general formulation for the quasi-longitudinal and non-deviative approximations. So under the approximation that we're kind of ish going along the magnetic field, that's what the quasi-longitudinal means. Non-deviative means we're only looking at just typical absorption from the material. There's another mechanism of absorption called deviative absorption that we're not talking about right now. The curves shown with different colors as indicated in the feature legend, in essence, it demonstrates the possibility of approximating the real portion of the index of refraction with this mu ordinary longitudinal. So this kind of reduced version of it, right? So the whole thing is that we're looking at this easier to calculate reduced version. And so the question is, can we get our true index of refraction values with this approximation method? And the same thing for the extraordinary, as long as conditions do not require changing the sign for x equals 1 as specified by the Booker rule. So x is let's go back to that Booker rule thing. Where'd we go? Oh, sorry. So, okay, so when signal frequencies is much greater than plasma frequency, x is much less than 1. When your signal frequency, oops, where to go? And it's the reverse for, yeah. So x is just, excuse me, the ratio of plasma frequency to signal frequency. All right. This fact is reflected in the similar curves for chi. Chi, again, is the imaginary portion. So again, with a complex number, you have your real plus I times imaginary, right? This is the magnitude of your imaginary portion. This is the magnitude of your real portion. So in this case, it's mu plus I chi. Right, is just the notation for index of refraction. Okay, in fact, when equation 5 is approximated to equation 8, so again, when we use that QL approximation, an assumption more limiting than QL approximation is made, considering the propagation is perfectly longitudinal. Okay, so you're assuming that your propagation path is directly along the same path as that magnetic field line. Now, to study the propagation, it is particularly important to investigate the conditions for which mu equals 0, right? So when does your real portion of your index of refraction equal 0? When ionospheric reflection takes place, right? So that's the point at which you're no longer just kind of propagating and slowly changing your direction. It's a straight up reflection, right? It's like hitting a piece of metal. You're bouncing off of it. Okay. In this regard, it is known that in the absence of collisions, even a small value of the theta angle is sufficient to ensure that the ordinary ray has a critical frequency of reflection for x equals 1. And the extraordinary for x equals plus or minus y. Only for theta equals 0 is the ordinary ray reflected in x equals 1 plus y, and the extraordinary in x equals 1 minus y. So get it, y is your measure of it's essentially the measure of the strength of your magnetic field to your signal. So it's telling you the frequency at which the electrons are doing this cyclotronic rotation around the magnetic field line. So that's essentially telling you what the magnetic field influence is on your signal, right? But that obviously depends on what angle. Hold on, let me do like this. What angle you're hitting this at, right? So this angle matters for how much of this cyclotronic frequency is going to affect the signal as it's moving through this, right? So this is perfectly transverse. If I go like this would be perfectly longitudinal, right? So this is the approximation they're talking about right now. All right. Is only the propagation can be considered okay. In other words, in the absence of collisions, it is only for theta equals 0 that the propagation can be considered with good reason to be. You move over. Perfectly longitudinal, right? So if the only time that you're in this condition is if this angle here is 0, right? That makes perfect sense. Okay. If the condition x approximately equal to 1 is not verified, propagation occurs in quasi-longitudinal conditions. So that's where the angle is close to 0. However, the same reflection conditions of perfectly longitudinal propagation occur only if omega c over nu is less than 1. So omega c is the collision frequency. No, wait, nu is the collision frequency. What was omega c again? All this notation. What was omega c? Give me. I can never remember these things. All right, nu is the collision frequency. Omega c is assuming p. Where's omega c? Oh, that was the critical frequency. Where was the critical frequency? It was around here somewhere. The critical frequency was defined somewhere over here, if I remember correctly. Okay, nope, not there, nope. I know it was defined here somewhere. I'm going to find you. Oh, critical frequency, where are you? What? Hold on. All right, we're gonna do this the hard way. Give me 1 second. I will find this. Blah 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 blah. Nope. Wait for it. Where the bloody hell? I know we saw it because we talked about it. I remember talking about it. Where the hell is it? What the poo? Okay, here we go. Here it is. 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 I told you we did it. Yeah, it was just because they sort of buried this equation, and it wasn't like a numbered equation. Okay. Okay. So the critical frequency, omega c, is omega b over 2 times sine squared theta over cosine theta. We'll say it's to achieve continuity if omega c is greater over nu is greater than 1. The positive sign. Okay, so once frequency is defined. All right. Z equals nu over omega, so that's collision frequency. Okay. The two refractive indices, although the choice of positive or negative sign, which must be decided, it's called Booker's rule. Okay. So omega b is the gyro frequency here. So the critical frequency is the gyro frequency over 2. Okay. That's seriously. Oh man. Okay, yeah. So the critical frequency is essentially a function of that gyro frequency that we talked about and the angle at which you're impacting the magnetic field. So you can think of it like that, right? It's just a relationship between those two. Ooh, I went way too far. Hello? Okay. Yeah, I just that should have been a numbered equation. Sorry. I mean, yes, it's my fault. I should have remembered where that was. But at least I remembered that we saw it. So I'm gonna call that a win. I wish he hadn't buried that. But anyway. Okay. So the same reflection conditions of perfectly longitudinal propagation occur only if omega c, so that critical frequency, over the plasma collision frequency is less than 1. This can be verified by observing the graphs of mu ordinary and extraordinary. So that is, I think, in figure 1. Right, so this is figure 1, right? This is figure 1. So if we look, that's the that's this value here, right? That's the critical frequency over nu, right? So this is oops, that's not what I meant to hit. There we go. So these are, as that goes way super high, you get this deviation between the approximation and the reality. That's really hard to see because they picked really poor ways of plotting these things. Right. And so as that gets bigger and bigger, the this discontinuity gets larger and larger, right? Okay. So that's what we saw in figure 1. The same behavior is observed with chi. So both parts of the index of refraction do the same thing where they start deviating. All he's saying really is that as soon as your approximation stops holding, your approximation stops holding. I mean, if you distill it down, that's essentially what he's saying. But obviously, in this case, he's talking specifically about where that limit is, but functionally, it's I think I need to just use it. That quote has got to be the end of every paragraph of my dissertation. That's what I'm going to do. Every paragraph of my dissertation is going to end with that quote. We'll see how well that goes. Anyway, right. So all this shenanigans aside, essentially what he's saying is there are conditions under which these approximations hold, and you can use the approximate version of it that's easier to solve for. And, but if you go outside these conditions, they start deviating away from each other, which is exactly what you'd expect with an approximation. That's how they work. Okay. Fine. Therefore, even the range of QL, so again, that's quasi-longitudinal conditions, is very wide. The possibility of considering propagation to be perfectly longitudinal and approximating equation 5 to equation 8 is limited by the condition omega c over nu is less than 1, right? So as long as you're within that condition, it works fairly well. This is evident in figures 3 and 4. All right. These figures show, for example, that if x is approximately 0.5, the k ordinary and k ordinary long. So again, this is the coefficient of absorption, right? So it's telling you how much energy is absorbed. Deviate approximately, appreciably from. So these deviate from the more restrictive approximation. Only if x is much, much less than 1, so your signal frequency is much less than your plasma frequency, when the ray wave is assumed in propagation conditions away from the reflection, that k ordinary, that all of these things are equal to each other. So in other words, when you're in a situation where you're well within the region where your signal's going to be bouncing, right? If your signal frequency is less than omega p, that's when you can get these reflections off of it, off the plasma. So under the more extreme versions of that, right, when your signal's running away from it, as it's leaving that, after it's bounced off, you can say that these are all equivalent. I.e., general formulation, a more refined QL approximation, and usually employed non-deviative absorption provides similar values for local absorption coefficients. Okay. So in other words, that approximation does not hold under most conditions. There's one set of conditions under which it does hold, but all the rest, you can't really use it. All right. Generally, the Connell-based ray tracing has to assume the absence of a geomagnetic field. Conversely, the presence of the geomagnetic field has to be considered when computing absorption. The geomagnetic field was assumed at this value, 4.5 times 10⁵ Tesla. Absorption was computed for the ordinary ray along the ray path, and the ray paths were assumed to be lying along the magnetic meridian. The wave propagation along the magnetic meridian is the optimal choice for highlighting how much are or what are even large the difference. What? Hold on, we missed something. What did we miss? Okay. The wave propagation along the magnetic meridian is an optimum choice just for highlighting how much are even large the differences between the general formulation and the more refined QL approximation and usually employed non-deviative absorption. Does that sentence make sense to you? It seems like it's missing something, right? For highlighting, how much are even large? Does that sentence make sense? Yeah, I didn't think so, right? Hold on. Let me make sure we're not missing a page here. 1648 and 1647. We're not missing a page. There's like a missing sentence or something here. Anyway. However, this is kind of interesting. So I would like to take a highlighted look at these. So these are the typical kinds of ray paths that you would get if it's published. Fine, it's fine. There are never any errors in published papers. Right. So these are different types of ray paths that you would see for different frequencies, right? So this is, you can see the stuff that's reflected at like the bottom of the F region over here. And then you have stuff that's reflected at probably FOF2. So I'm guessing it'd be like this if you were to plot the electron frequency. So you can just see how as your frequency increases, right? This pathway is changing because you have to get to higher and higher plasma frequencies, and the plasma frequency still is here increasing, before it will reflect or super refract technically, but before you get the reflection to the point where you can get signal down here, right? So this is why you can have a minimum usable frequency, because eventually it'll just start doing this and it'll go off to space. So if you're above the minimum or the maximum, sorry, if you're above the maximum usable frequency, you'll no longer reflect down, right? So this is lower frequency, higher frequency. Okay. And this is 1,000-kilometer link at different frequencies. The simulations are based on the Eikonel equation using IRI derived ionosphere for June 5th. Sure. Assumed either low or R12 equals high solar activity. Both low and high paths can be distinguished. Okay. So what's interesting here, right? You can see the way that the it's true, yeah, it's trivial, exactly. No, it's extremely complicated, difficult to interpret, and not worth reporting. That's what it is. Yeah, it's kind of interesting. You can see how you start getting increases in electron density down lower in altitude. And so some of these reflection paths are coming down here, but you also have these uneven pathways, right? These aren't all nice and smooth. So you have some unusual effects that go on. And all of this, of course, is going to affect how much absorption you have, right? So down here at these lower levels, what that's primarily going to be affecting is your absorption down at the D and E regions, right down here. So you're going to see much increased absorption. However, what's interesting, right, is this particular pathway, right, this lower path, propagation path that you see, is much less distance than this propagation path. So you'll actually have some frequencies where you'll have an increase in your signal frequency amplitude, right? So you'll be seeing more energy from these because the actual travel distance is less. So sometimes different frequencies will be affected differently depending on how the ionosphere is changing. So you can see how this all can get very complicated and interrelated and silly shenanigans. Anyway, I just thought this was neat because it's kind of showing you what those ray paths look like. So again, these are how your radio waves are going to be traveling through these different ionospheres. and how much the solar impact can be on some of these ionospheres. And if the solar impact is too high, all of this will be absorbed. You won't get nothing. Because your collision frequencies will get so high that all of your energy gets absorbed. So we're going to ignore that sentence and go on to the next one. The low ray paths occur at a narrower HF band, 3 to 11 megahertz, assuming low solar activity, and a wider HF band, 2 to 14 megahertz, assuming a high solar activity. Okay, makes sense. The apogee, because what's happened, so what's happened at this this high solar activity, you've had an increase in your so if you were to plot what your electron density looks like, right? So if I go up here, oopsies, your electron density might look something like this, and then it would go up to here and go down, then it would go up and then like that, right? Well, here you might have it be it might be even lower, so it's going here, and so you have, right? So now all of a sudden you've got a higher electron density here that's able to reflect higher frequencies than it could here. So this lower peak is called FOE, and this higher peak is called FOF2, because this is the F2 peak, this is the E peak, so that's FO, F2 and FOE. So the question is, you know, you'll get a wider frequency band that's able to reflect off of there. Anyway. All right, assuming high solar activity. All right, the apogee of the low ray paths reaches a similar altitude, h equals 100 kilometers for both solar activity levels. Indeed, that altitude corresponds to the bottom of the E layer, reflecting the low paths as a mirror. Instead of the high ray paths occurring in the higher HF bands, 9 to 14 megahertz. So again, yes, they do. So solar flares do a few different things. You have increase in UV and X-rays, right? And so that can that will affect how much of the stuff down here is getting absorbed. That's number one. Number two is you have this whole slew of charged particles smacking into the ionosphere, right? And so, or not smacking into the ionosphere, I'm sorry, smacking into the magnetic field lines, right? So what happens is the Earth's magnetic field, let me find a good place to draw this. Right, so your Earth's magnetic field, so if here's the Earth, the Earth's magnetic field would look something like this, and then it does this. It sort of trails out around back, right, because it's being pushed by the it's being pushed that way, right? So the particles, the charged particles are coming in from the sun this way. What they'll do is they'll start gyroscopically moving along here and then depositing at the top, and this is where you get your auroras, right? Or all those charged particles smacking into the top and the bottom of the atmosphere, right? But also, if you get enough of them, it starts compressing this B field in. And so your B field concentration will increase. In addition to the, you have a bunch of extra charged particles moving along the B field, and you have the increase in in energy that's being deposited. Also, some of it will punch through and will get down into the atmosphere itself and will deposit more energy within the atmosphere and will increase your rate of ionization events occurring within the atmosphere itself. So all of these effects are kind of occurring at the same time. So yeah, solar activity obviously is the driver of all of this, but it does it in a number of different ways. That the solar wind, and there's a few other things, right? You can get galactic rays will come in as well. We'll do some other stuff, or you'll get high energy galactic particles as well. They'll deposit energy in different ways. Yeah, so there's a few of these other interacting elements to it as well. But yeah, so as we were saying, so up here, these frequencies are too high to reflect off the bottom of the E layer, right? They're reflecting off the F region. That's much stronger. During the day, I should say, that's much stronger. Similarly, for solar activity levels, the apogee of the high ray pass reaches a higher altitude, as you would expect, right? It doesn't reflect until it sees a much higher electron density. H is greater than 200 kilometers throughout that band, right? Assuming low solar activity and a lower altitude, especially for the lowest HF. Okay, 9 to 11 megahertz, assuming, okay. Blah, 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 blah. Sure, right. He's just describing the changes in those two things. Okay. Indeed, the F1 layer, which appears for both the solar activity levels, is characterized by a higher critical plasma frequency, assuming a higher solar activity. So there you go. It's got more plasma. Interference between what? So the extra, so like galactic rays can cause interactions with the charged particles. So it's not just photons that are coming, remember. It's also this whole slew of charged particles that are being shot across. Especially in a solar flare, right? Solar flares have huge the solar wind increases a huge amount. In fact, you get these shock waves, right? Because they start accelerating faster than the speed of sound within this medium, very diffuse medium. Okay, sorry, I'm bad at joking. I apologize. I recognize a joke. I'm bad at things. Most things, in fact. Okay, indeed. Okay. F1 layer, which appears for... Okay, we talked about that. All right, the corresponding absorption computed for the same 1,000 kilometer radio link at different frequencies is shown in figure 6. So this part is also interesting, right? These are things that I actually personally really care about. I want to know... Yeah, that's true. Yeah. They do interact. Sorry, my brain was like... I was like... Never mind. Of course they interact. Whew, I was like, you're right. They're not charged particles. They don't interact. Don't worry about me. I know science. Trust me, bro. I know science. See, this is why you guys come here for these deep cuts. Oh man. Anyway. So these are the um, these are the loss curves that we're looking at here, right? So this is how much absorption are you getting as your signal is moving through this ionosphere. And this is kind of what I'm really interested in, because my data that I'm using for my research is literally just this bounced signal, right? That's and I'm calculating the absorption that occurred to the signal as it went through the ionosphere. So this part actually really matters. So this lower level here is with just the non-deviative typical absorption that you'd expect to see, right? And then the upper one is if you include the deviative absorption. If you notice, as your frequency decreases, the amount of absorption that's deviative, it becomes more and more important, right? Also, I would note this is in decibels, so this is log scale. And you can really see the difference here between the low and high solar activity, right? You're going from 40 dB of absorption at your highest to 180. So, yeah. So you're seeing dramatic changes to the levels of absorption as you go into these higher higher solar activity areas. And what's this? Oh, this is the upper band. This is just the upper band, right? So this is just kind of zoomed in at the upper region. And this is talking about the difference between the QL approximation, so again, that quasi-longitudinal approximation, compared to the non-deviative. And you can see here that it's pretty good at these higher frequencies, right? That's where that X is approaching 1, and it's less good as your frequency your signal frequency decreases. All right. Oops. All right. Okay. Indeed, aside from the reflection due to the bottom of the E layer, the low ray propagation is just non-deviative, such that the real part of the refractive index can be assumed to be unitary, mu equals 1. I think we missed something. Did we miss something? We did miss something. Sorry. All right. Firstly, the refined QL approximation and the usually employed non-deviative approximation provide comparable values for low ray paths throughout the whole HF band. Indeed, aside from the flexion due to the bottom E layer. Okay. Okay, secondly, the refined QL approximation provides more accurate values than the usually employed non-deviative approximation for the high ray paths, especially for the lowest HFs 9 through 11 megahertz. Indeed, the high ray path propagation in the F1, F2 layers is even deviative. So essentially, deviative absorption essentially happens when your wave propagation gets slowed down in the medium, right? And it starts going off at weird angles. It deviates from the expected angle, and typically it deviates up and out into space, and so you lose signal. And that happens right at so-called cusps, which is right at the end of where omega equals omega p, right? So right there at that cusp area is where you tend to get the most deviative absorption. That's really, it's really like a function of that resonance that we kind of talked about. That's built in there. Anyway, okay. So the high rate paths is even deviative when that the real part of the reflective index must be assumed to be less than UD, less than 1. Thirdly, the refined QL approximation and the usually employed non-deviative approximation provide underestimates compared to the general formulation, assuming either low or high solar activity, and both the approximations to the general formulation, especially at the highest HF. Wait, what? Let me read that again. Thirdly, the refined QL approximation and the usually employed non-deviative approximation provide underestimates compared to the general formulation, right? So again, this black line is the general formulation. This red line is the non-deviative assumption. And the in-between one is QL, right? That's the quasi-longitudinal. So both the QL and the non-deviative provide underestimates compared to the general formulation, assuming either a low or high solar activity. And both the approximations to the general formulation, especially for the highest HFs. Again, that sentence doesn't make much sense, but essentially what it's saying is that both of these approximations that are often used are not really good. Indeed, the general formulation takes into account the deviant and non-deviant propagations occurring across the E and F1, F2 layers, where the real parts of the refractive index is generally assumed as mu is less than or equal to 1. However, figure 5 and 6 prove our ultimate purpose of underlying that, at any rate, some of the practical applications, the more refined QL approximation can be used, while the usually employed non-deviant absorption can lead to significant errors. All right, so in all of this, essentially what they're trying to do is they're saying, hey, we came up with this improved QL approximation, and it does a little bit better in some conditions. Now, again, this is log scale, so a little bit better could be a lot better, but it's not that much of an improvement between the two. It's maybe, hold on. If I'm looking at this, you maybe got like 0.75 to 1 dB improvement in estimation. Okay. Summary. The main results can be summarized as follows. Let's see how they summarize these. 1. Commercial mathematical software tool packages make it easy to obtain exact values of your absorption coefficient, which are obtained from the imaginary part of n and applying the Appleton-Hartree equation. Yes. 2. The local absorption coefficient K, calculated by equation 12 and setting mu approximately equal to 1, is an acceptable approximation only for x much less than 1, right? So when your signal is much less than your plasma, your signal frequency is much less than your plasma frequency. 3. A better approximation for K ordinary longitudinal can be obtained from chi ordinary longitudinal, which are calculated from equation 8 without setting this approximately equal to 1. The expression of such QL approximation, nothing complicated, can usefully be implemented in a software program running on modern computers. So you can use this other approximation, although I really don't know why you would. Anyway, we've just said, literally, he just said in the first one that, hey, modern computers can do the full version of this. And he's like, oh, well, you can also use computers to do this approximation version. Anyway, it's important to consider the application of Booker's rule applied. Okay. So, in summary, Here's what I think happened in this paper. They tried to do this thing, right? They're like, oh, we can do this QL approximation and it'll be better than the typical approximation that's used, right? And they did all the shenanigans, got all these results, and they said, you know what? Doesn't actually do that much better. And it's not that much easier than using this the more general version. So let's just use that. To me, that's how this reads. They're doing their best to make the best of a null result. Which again, in science, it's fine to get a null result, but when you're trying to publish papers, it's less fine to get a null result. So that's if I had to guess, I believe that's what happened. However, for us, it's actually somewhat useful to take a look at and just go through the mechanics of all of these different pieces, and helps us understand a little bit of what's going on. So that's why it was helpful to go through this paper. Yeah. The next paper that I want to start this guy's also using quasi-longitudinal approximation. Well, these plots look familiar. I'm sure ray tracing. Oblique sounding of absorption. So I kind of picked this paper because I thought it might be good as you can see, it's a lot of text, right? So it might be good as an overview and a reconnection with some of these things. These are the approximations that we talked about in the last paper. So is it useful? Well, here's the question. Okay, here's a valid question. Would you guys want to go through this, especially like the ray tracing piece, to see how that looks? Do you want me to bit piece through some of this stuff? So do you want to go through the whole thing? Do you want to try and cut this up into some of the interesting things, or do you not want to do this at all? We can just go on to a completely different subject. Let's see. What's this guy? Research. Well, we've got a few things. Well, here's the iconal modal for one layer ionosphere. If you have a specific paper you'd like to go through, we can certainly do that. I've got, let's see, I have some other ones sitting around here. So there's this one, which comes from bioinformatics, but is talking about bias error estimation in validating different models, which for me is useful because I have like a dozen different models going on. That's true. We could take a look at that. That might be a good idea. We already went through those. Let's see. Any of these we didn't go through? The last one, yeah. I read the articles yesterday about antiferromagnetic terahertz spin torque oscillators, eigenmodes, and emergent massive scarons. I think the last one will be interesting conceptually. The abstract resonates with you, but still specific to the field. Yeah, I can certainly give it a try. If you drop the title in chat, I can take a look at it. And I'll let you know. It might be out of my depth. What is it? Oh, because you tried to put a link, probably. Let me see. Let me see. Can I see it in here? What did it do? What did it do? Okay. One moment, please. Let me go find it. Kablam! Here it is. View PDF. Let's see. Let's go over here. Okay. And now we want to print this to OneNote. There we go. Print. Bloody hell. There we go. Let's see. Okay. Doesn't look too bad. We could give this one a try. Yeah, it was open access. It popped up in archive pretty good, pretty easily. Oh, Johns Hopkins University. Neat. They have a really cool whole lab area called Applied Physics Laboratory. They do a whole bunch of really cool stuff there. So how about this? Zephyr, I saw you wanted to try the bias one. I think that will also be interesting. Why don't we go through, we'll do this one. We'll try this one out today, and then we'll set the bias one to be our next paper after this. Because yeah, I think the bias one is generally applicable, regardless of what field you're specifically in, because it's talking about how do you compare different models, right? And if you're building bias in different models, how does that, or how do you figure out what I think it's talking about is how you figure out what's the best model, what types of bias you have. Okay. Yeah, absolutely. We'll take a look at it and see what we can find, and we can do some ancillary looking up as well. That's always a thing. We can go around and ask the interwebs if it has any more information than we do. Okay. I'm always willing to give it a try, and I'm always willing to say I have no idea what's going on. So let's give it a try. Okay. Introduction. Topological solitons and magnets attract the interest of both physicists and engineers. Their stability on the one hand and mobility on the other makes them attractive for storing and processing information. Current experimental efforts are focused on domain walls and skyrmions, previously known as magnetic bubbles. A thorough understanding of the dynamics of the topological solitons and magnets is a prerequisite for the success of the efforts. Since this is more your field, can you give a 2-bit definition for these terms? For both the solitons and the skyrmions. I am so glad to have you on these streams, by the way, because this is awesome. Again, this is something that's so beyond what I would normally get to, and to have you in here with your knowledge base, so cool. Scare me on. Yes, yes. So there's like the uniform versus the sort of source. Yep. Okay, so is this acting kind of like a magnetic source field or field source kind of thing versus this more isomorphic magnetic direction? And are these spin directions or are these magnetic field lines? Gotcha. So this kind of like wee. How it does this like cascading. It looks like this doing wee. Spins or magnetic moments. Okay, cool. Okay. So yeah, so these are each different atoms then within within a magnet, I'm presuming, right? And so you're talking the net spin of each of these of the electrons of each of these atoms. Or I'm sorry, it's the net spin of is it the nucleus net spin or is it the electron spins? The electron spins. Okay, yeah. So you have an asymmetric total set of electron spins, right? So in a nuclear spin is negligible here. Okay. So in a non-magnetic material, and you can tell me if I'm going off the deep end here, right? In a non-magnetic material, these spins are kind of in random directions. So you don't end up with sort of what's it called? Net direction for these spins, right? In a magnetic material, these spins align in the same direction, and so that's what produces your overall magnetic field. Yeah, right. So the temperature, the spin. That's why you have the it's not critical temperature. There's a name for the temperature that will destroy a permanent magnet, right? You can heat it up to the point where these spins can start moving around independently, and then they'll like randomize themselves. But in a permanent magnet, right, they would all be pointing in the same direction, which is why overall you end up with this net magnetic field. But this is just a specific configuration called a Skymeron. Scamerion. Scare me away on. Critical quest. There you go. That's it. Yep. Right, which is why don't heat up your permanent magnets. All right. Cool. Thank you very much. I really appreciate it. Okay. So, a Skymeron in a two-dimensional ferromagnet with continuous spatial coordinates, which again, this is what's pictured here, is a soliton with a non-trivial topology of the magnetization field, right? So this is clearly a non-trivial topology, right? You have this, the whole thing is set up in this sort of field mechanism, like it's almost like a source up and then back down, right? So you have this whole array of directions. Oh, interesting. So it's not just a random alignment, then they're fully anti-aligning themselves. Stable configuration which can travel along the sample. Oh, that's cool. Okay. Okay. That's really neat. So it's the spins are kind of, the spin direction is acting as the transportation medium for the wave. Oh, that's so cool. Okay. Thank you. Right. So this is kind of like a point version of it. Is that what I'm getting out of this? Like I'd imagine a soliton is kind of a would be a plane wave in some way, would it? And this is almost like a point source moving. Or do they all kind of move around in this sort of point-wise way? It's not linear. Okay, so I'd imagine you have some kind of wavefront. I'm sorry, I'm analogizing this with electrodynamic, electrodynamic propagation, wave propagation. So I'd imagine you end up with some wavefront property. It's a wave packet. Okay. And that wave packet is, I presume, because this looks like. Well, tell me if I'm wrong. Is this a wave packet, or is this like a single atom that's at the center of it, right? And that's moving, where the spins are moving like this. So is this kind of like a single atom source? It can remain stationary though. Okay, so you can kind of lock in it's the whole configuration. Oh, cool. Nice. Okay. So those spins can remain frozen. Are they kind of, sorry, I'm sorry for asking so many questions. I apologize. So do you have oscillatory motion in the spins, or will they just be frozen in those vector directions and just kind of sit there? I don't know, that's stuff I'm learning. I like learning things I've never really worked with before. It's cool. That's why I try and do the streams. Mostly frozen if you don't disturb them much. Very neat. Cool. Okay. Right. So non-trivial topology is a magnetization field. Normalized for convenience for unit length. The magnitude is 1. Sure. Right. A smooth magnetization field approaching a uniform state at spatial infinity is characterized by an integer topological invariant defined as the degree of mapping R onto M. Okay. So Q is 1/4 pi. So we're integrating over our entire 2D field here of m dot mx cross my. Okay, so mx cross my is going to be yeah, right? So that's going to be in the z direction. So then you're taking the projection of m onto the z direction based on how it's changing in the x and y. Is that correct? It's kind of what it looks like. It's the projection of it's the projection of m onto the essentially the cross product of the velocities in x and y. Q is something like total angle, which spin accumulates from center to infinity, but this is 3D analog. Okay. So you just set some 0 on the angle on these the angle of these spins, and then you just kind of integrate over the whole thing. So I assume downwards in this case is 0, right? For each individual one, you just kind of integrate along that. Right, because this is going to be 0, right? Your cross product there is going to be 0. So the whole thing's going to be 0. Okay, that makes sense. Yeah, it makes sense. Okay, states with different Skymaron numbers, Q, such as figure 1, cannot be continuously deformed into one another so long as the boundary condition M approaches constant as R approaches infinity is maintained. Okay. Fair enough. Skymarons, stable isolated solitons with Q plus or minus 1, exist in a number of ferromagnetic models, including pure SO3 symmetric Heisenberg model, as well as an anisotropic variations with additional interactions. The chiral, I'm not even going to try and pronounce those names, terms, and long range dipolar forces. Okay. Names and long range. Right, because if you have a long range dipole, you're going to have. Okay. Setting aside the rather complex question. Wait, where's our quote again? We need our quote again. Question of Skymaron energetics. Okay, how much energy is in these things? We assume that an isolated Q equals 1 Skymaron in equilibrium is centered at the origin and has a round axially symmetric shape. So, yeah, exactly what's pictured here. Right. This is 0, right? And it's symmetric around the axis. Okay. Okay. Under these assumptions, it can be parametrized as follows. Theta R is big theta R. What's big theta R? R and alpha are polar angles. Theta are spherical angles. Okay. No, I get it, but what's big theta? Because pi. What is big theta here? R is different. Last R is just in plane radius. Oh, that's it. Right. Yeah. Yeah, this is R. Oh, I see what you mean. Okay. Just radius rather than the big theta describes certain types of solution, but it's the same angle physically. Okay. Gotcha. And phi of R equals alpha plus constant. Here R and alpha are your polar constants, your polar coordinates. So that's right. Alpha and R are your polar coordinates, and theta and phi. That's usually theta, and this is phi in spherical coordinates. X equals okay. Yeah, this is just a complex number. M plus IM equals sine theta, e to the I phi, and mz equals cosine theta. Okay. So it's just different. Yeah, it's just transformations. Okay. So Skymiron dynamics. The dynamics of a magnetization, M as a function of R and time, is described by the Landau-Lifshitz equation. S, where S is the local density of angular momentum. Okay, so the local density, the change over time of density of angular momentum, right, is minus m cross delta u delta m, where u is the energy functional and du dm is the functional derivative. Okay. So it's kind of the energy flow. Tell me if I'm wrong, right? This is essentially the energy flow as m changes. And so this is telling you how the density of m, which again is your magnetization field. This is telling you how the density of your magnetization field is changing over time as energy flows. Mean field of a certain spin, its dynamics depend on surroundings. Yes. Right. So S of MR is the local density angular momentum. U is the energy functional, right? So is the functional derivative. So that's how the energy is changing. So it's kind of giving you how the mean field changes over time as your energy is moving around. We neglect the damping effects. Equation 4 is nonlinear partial differential equation with precious few exact solutions. Surprise, surprise. All right. A general method to find an approximate solution for a moving ferromagnetic soliton. So again, that is perpendicular to M. Yeah. That is, that's a good point with a cross product. Yep. And inverses direction too, which is interesting. But anyway, so M is always going to be perpendicular to the direction of movement of the energy. Oh, so that means you can, like, if you start screwing with some of the energy pieces of it, can you use that to change your M value? So if I start putting change of M dm doesn't change the magnitude of M. It only rotates the vector. Oh. Interesting. Okay. Right, because it's not really changing your spin values, right? Your net spin is still the same, isn't it? And it's just sort of changing which directions they're aiming. That sort of net aim of the spin is. Okay. Fair enough. Okay, so A general method to find an approximate solution for a moving ferromagnetic soliton was suggested by Thiele. Under the assumption that a moving soliton preserves its shape, okay, we may express the magnetization field, M as a function of R and T, at an arbitrary time T by rigidly translating the initial configuration over, right? So we just literally move it some distance, right? So we take some vector R along that plane. So if we were to go back to here, stupid thing. If we go back to here, you can imagine, oops, that is not what I meant to do. There we go. Right, you can imagine this singular point sort of just moving around to some other point. So that's essentially what it's saying. The shape isn't changing, but it just sort of moves around. Okay. So the time evolution of the displacement is given by the Thiele equation. So that's g cross dr dt. So this is the velocity. What's g? The gyrovector g is perpendicular to the film plane. The magnitude is proportional to the Skyron number. Okay. Plus F, and F, the second term F is a Thiele equation, represents all other forces acting on it. Okay. So, right. So it's just kind of a conservation, the equivalent of a conservation of momentum equation almost, right? If you think about it. Right? It's saying that the movement is essentially just equal to the force that's on it. This is almost this is essentially an F equals ma equation. Tell me if I'm wrong, but that's kind of how I'm reading it as a easy off the top. Turn nonlinear. Yeah. So it's just saying it's moving as the net force that's acting on it. Okay. So the gyrovector G is perpendicular to the film plane. The magnitude is proportional to the Skyron number. That's what we said there. And the spin density S. So it depends how many of these things are packed together, right? So the more packed together these things are, the greater this gyrovector R, because you kind of are summing more of these individual spins together, right? So your net spin is increasing. Okay. So that makes sense conceptually. The second term F is the sum of all forces. For instance, the position dependence of a soliton energy, U of R, creates a conservative force, F equals negative du dr. Okay. Sure. Yeah. We're just turning this into classical mechanics. Hey, it moves around, kind of like you could think of it like almost like a particle moving around this magnet. Spin density is constant. Yeah. That makes sense. Okay. So numerical studies of Skyron dynamics have uncovered significant deviation from Thiele's theory under fairly mild driving forces. The failure can be traced to breakdown of the rigidity assumptions in 5. Or the rigidity assumption 5. Deformation of a soliton makes the very definition of its position R ambiguous. Different conventions for R can yield dramatically different trajectories. Yeah. So this approximation only works for it falls apart at a certain point, right? So okay, position defined by Skyron density. Pep Nicoliu and collaborators, God, I butchered that. Pepeni Koliau and collaborators define the sky mirror position R as the first moment of the sky mirror on density, right? So that's okay. Integrating R divided by okay. Sure. And then the trajectory R sky of T shows excellent agreement with Thiele's equation. For example, when the non-uniform magnetic field is suddenly turned on, exciting a constant Zeeman force, F, on the skymiron, the soliton moves in a straight line with a constant velocity perpendicular to the applied force. Right? So it just acts like you're applying force to it. It is not a coincidence that all right, so the movement of the skymiron satisfies the Thiele equation, even when the rigidity assumption is violated. Our sky is directly related to the linear momentum of the skymiron in 2 dimensions. Okay, which is valid for arbitrary deformations of the soliton. Okay, so it's directly, so the rigidity assumption is directly related to linear momentum. Which is valid for an arbitrary deformation of the soliton. When skymiron is driven by an external force, its linear momentum changes, and it follows immediately that R2 satisfies the Thiele's equation. Okay. So if we use this other definition for kind of the location, we're kind of, so what we're kind of doing here then is it's sort of like, okay, this is a really bad analogy, but bear with me here. We're sort of trying to figure out how to cross the quantum non-quantum barrier. Barrier. So you're trying to say, all right, if you're looking at a wave packet, but you're trying to give it something like a singular position like you would see in classical mechanics, which is really what you're sort of doing, right? You're trying to squint your eyes and say this looks like classical mechanics. How do you do that for something that does not act as a classical particle? Right. But what you're looking at is deforming, right? It's acting like a more spread out object, because it's not just a singular particle moving around, right? So because the shape is changing, in the same way you can think of like a wave packet diffracting or something, right? It's doing this change. You're still wanting to say you can sort of follow the particle from classical mechanic viewpoint, but you just have to shift what the location means. Right? So you're redefining what location means in these terms so that in the classical viewpoint from which you want to run these calculations, because it sort of acts like it, you can still run them, even though the shape of it is warping and changing in a way that's non-classical. That's sort of, I guess that's the analogy, and you can tell me how apt that analogy is, but how I'm seeing the analogy of this, what's going on here with this approximation. Okay. Which is valid for arbitrary definitions of soliton, right? When a skymiron is driven by an external force F, the linear momentum changes at a rate of dp dt equals F, right? It follows immediately that R skymiron T satisfies the Thiele's equation. So then everything looks pretty and falls back to the classical mechanics version of F equals ma. Excuse me. Position defined by out-of-plane magnetization. Another common definition of the skymiron position uses the out-of-plane magnetization, mz, relative to the ground state value of mz equals -1. So again, if we look at if we look at our two different portions here, here's where you don't have a Skymaron. So the magnetization of all of them is directly into the negative Z direction. So here, this would be plus Z, and in below would be negative Z, right? So they're all pointed in negative Z direction, and then you just normalize it and say, well, that's equal to 1. Here, you can start looking at, well, what portion of the field is not equal? You know, where is my MZ not equal to -1? And I can use that to locate as a form of location. It's going to be like, you know, an area like this, right? And I'd imagine it kind of looks like something like a distribution like this, you know, obviously in 3 dimensions, right? So it's going to look like you know, kind of like a packet like that, and that can move around. So that's if you define it by the magnitude of MZ greater than -1, right? I'd imagine that's kind of how you do it. Okay. Using the outplane magnetic field MZ relative to the ground state, right? As the statistical weight, Rmag. Okay, so you're integrating MZ plus 1 times, right? There's your R, right? So for example, the magnetic, so this is just kind of a normalization. For example, the magnetic dichromism of X-rays allows the mapping of the magnetization component MZ of R and T with sufficient spatial and temporal resolution to determine the Skymaron trajectory. Magnetic dichromism of X-rays allows the mapping. Dichromism. That's the word. The magnetic dichromism. Dichroism of X-rays. The magnetic dichroism of X-rays. I don't know what that word means. Allows the mapping of magnetic portions of magnetic component with sufficient spatial and temporal resolution to determine the trajectory. So I assume that's a what's it called? An experimental method of mapping the location and trajectory of the Skymarons. But wouldn't that inject a lot of energy into it if you're hitting it with X-rays? It feels like that would have feels like that would be a force on there. It's fine. Okay, that's fair. All right. The numerical simulations of Rmag of T shows marked deviations from Thiele's equations. A suddenly switched on Zeeman force generates cyclodal trajectory. A cyclodal trajectory, so going round and round, I assume. A superposition of the linear momentum and the cyclotron orbit. Okay. An excellent description of this trajectory is obtained following Thiele equation with an interim term. So MA equals GR plus F, or what's the interim term? Oh, okay. So that gives an equivalent mass. Well, that's cool. Oh, yep. No worries. Thanks for joining in. I appreciate it. As we've taken a left turn into a completely different area, which is kind of cool. Okay. So what's going on differently here? So an excellent descriptive trajectory is contained by endowing the Thiele equation with an inertial term. Okay. We have inertia now. right? Because we have this equivalency to M, equivalency to mass. So again, if you notice, hold on, all we've done is we just did MA. The mass is emergent. Yeah. The empirically introduced Skytron mass M determines the frequency of the cyclotron omega. I feel like M is defined by this, right? Because M is kind of like the inertia of the switching speed of the spins. Like, I'd imagine that, right, you're going to get some resistance to that changing of spin direction, right? So that's going to be when you take that over the entire area, right? That looks kind of like a mass, is what I'm imagining, right? It's resisting the shift in spins up to a certain point, so it's going to act like inertia because it's the what's it called? It's the rotational inertia of the spin that's resisting the change in direction, right? And that on the larger group of things acts like a mass that doesn't want to be moved, which is really cool. I like that. That's really cool. So again, for everyone else following along, what I'm talking about is these spins are kind of what's it called? Are kind of the equivalent of rotational so no mass is allowed and no inertia. Yeah, because it's not actually mass and inertia, right? It's really just spin direction. But the spin direction is has, you know, it's like it has gyroscopic stability almost, right? And so it doesn't want to switch to move around to switch how it's aiming. And so if there's a force that's going to switch it, it can happen, but it's going to take a certain amount of force to overcome that. And it's the equivalent of it is analogous to. So here's what I would say, and tell me if I'm wrong with this. It's not mass, but it's analogous to mass when we're using this whole set of classical mechanics that we're talking around here is an analogy, right? It's an approximation where we're saying this looks kind of like classical mechanics if you squint. So how far can we take that looks like into actually describing what's going on, right? So you're right, when you go and dive into it through those equations, there is no actual mass here. It's actually right, because the Skymaron, if you think about it, what is the Skymaron? It's this setup of spin directions. So if this is going to move, if this Skymaron is going to move somewhere, that means that the spins over here have to change their direction, right? All of these spins have to change their directions. So any kind of gyroscopic force that wants to keep the spins in the directions where they are is going to resist that movement a certain amount. And so that's analogous to mass resisting a force, or, you know, momentum, mass having momentum. At least that's how I'm seeing it. Again, that could absolutely be wrong, but that makes sense in my brain. That's Yeah, that's how my brain is trying to put it together. So, right. Um, let's see, what time is it? Ooh, almost 2 hours. Okay. So what we'll do is we'll go through this. Oops. I thought I was on this. We'll go through this section here, 1.5, and then we'll stop for today. And then next week we'll do the rest of this. Because I have to go out and get lunch for the whiff. The whiff. Anyway. Okay. So right. So the origin of the mass can be traced to the origin of the inertial mass. I'm sorry. The origin of this mass can be traced the origin of the inertial mass to the deformation of the skymaron that increases linearly with the velocity of the driven skymaron. The energy cost is quadratic in the deformation, and thus the velocity effectively produces kinetic energy of 1/2 mv squared, right? So that's our good old-fashioned kinetic energy. Emergence of inertia in ferromagnetic domain walls in some... I'm sorry. Let me read that again. Emergence of inertia in ferromagnetic domain walls in the form of kinetic energy was first proposed by Doring and has been observed experimentally. And Ivanov and Stefanovich applied this line of arguments to skymarons. There is a compelling reason to prefer one definition. Oh, is there? Is there a compelling reason to prefer one definition of skymaron position to another? Krakyuk et al. Have recently argued in favor of our sky going as far as to declare our magnetic not physically sound because it does not describe the skymaron displacement in the sense of the traveling wave model. We're not convinced by this argument. Okay. The assumption of rigid displacement has no profound principle behind it. It was adopted by Thiele for a practical task of describing a steady state motion of a solitron, right? So again, they're saying, hey, this kind of looks like a particle moving around, so we're gonna see if it fits the classical mechanics equations. A closing remark in his letter clearly states that this approach, quote, may be used as a first approximation beyond steady state situations. Thus, we see no fundamental reason why our sky should be preferable to RMAG. In our view, both definitions can be useful. Our sky is clearly more convenient because of the simplicity of its dynamics. However, it is RMAG that is experimentally accessible at the moment. This situation is entirely analogous to the dynamics of a massive charged particle in the presence of a magnetic field. The physical position of the particle, the analog of RMAG, exhibits cyclotron oscillations on top of the steady drift in the direction orthogonal to the external force. The guiding center of the cyclotron orbit, the analog of our sky, exhibits a simpler motion without the oscillations. The guiding center is a useful tool in the analysis of low energy physics in the n=0 Landau level, such as the quantum Hall effects. However, it cannot replace the physical position of the electron if we want to include degrees of freedom beyond the lowest Landau level. Right. So in other words, oh, really? That's really cool. That's so cool. When you get to work, you'll be like, I know that guy. That's really awesome. Yeah. So long story short, we have a very complex system that's going on. That is a kind of a statistical system moving around, but it acts like a particle in classical mechanics. So for a at first look, that's just fine. That works absolutely just fine. But but then obviously, if you want to go more in depth on it, you need to get into the overall discussion more. Nice. That's so cool. That is legitimately awesome. So I'm gonna stop here for this Sunday morning papers. Because I have my paper to continue writing. We've been at it for 2 hours, which I think is a good amount of time. I did my best to understand what's going on. So thank you. I really appreciate it. And I really appreciate this paper. This is fun doing something that I've never done before. And that's really enjoyable. So thank you very much. We'll keep on cranking through this. And again, if there's anything more that you see, you're like, oh, we should talk about this, and this, let me know. Yeah, so next Sunday we will finish this paper, and then the Sunday after we'll move on to that other one that's talking about the different the comparing of different theories and how you select, or different models rather, and selecting a model, which is kind of a generally useful property. So yes, thank you again. I really appreciate it. Thank you for this paper. This is a lot of fun. Our next stream will be on Wednesday, when we will be reading again. So we will continue our reading of Terry Pratchett's book. Why am I forgetting the name of the book? The title of the book. Lords and Ladies. There we go. We will continue our reading of Lords and Ladies. Let me see if I can find anyone of interest to read. Twitch. Let me see what we've got going on. Browse. Anyone doing science and technology type things? Apparently there's DEF CON going on. Cybersecurity. What the flip is that? We've got an ant cam. That's fun. DEFCON 6 FFA. All right. DEFCON 3. Ooh, we've got NASA Space Stream. That's always fun. Yeah, I mean, it's just a random stream, but we can. Let's go take a look at space. Let's see if it'll let me. If it'll let me raid. I don't know if it'll let me raid them, but raid. They might have raids turned off. No channels, followers, only. Oh, it does. Okay, cool. Enjoy space. I am sending you off into the great beyond, the great black. So enjoy space. I will see you guys on Wednesday and then on Friday. Goodbye, everybody. Ooh.